Hello everyone, in this video we will visualize the velocity of a simple harmonic oscillator. In my earlier video I have shown that the displacement of a simple harmonic oscillator with respect to the equilibrium position is given by a cos omega t plus phi, where a is the amplitude which depends on initial position, initial velocity and the natural frequency of the system. Velocity is the derivative of the displacement, hence it looks something like this: minus v0 sine omega t plus phi, where v0 is the maximum velocity that the mass can acquire. So v0 is given as a omega, that is amplitude, into natural frequency. So the velocity also oscillates between minus maximum and plus maximum, and in this window we can see the object oscillating to and fro. So let's look at this system whose mass is half kilogram, spring constant is half a Newton per meter, and the object is displaced by 45 centimeters and it is not yet released. So this slider over here is for the time. If this timer is changed, so this is what we had seen in the last video. This is how the position time graph looks like. The position goes between right extreme and left extreme. So what happens to the velocity? Now the velocity will be plotted in this window, this graph. Also I will use the position palette. When the object is on the right side of the equilibrium position, the dot which represents the position or velocity will take a red color, and if the object is on the left side of the equilibrium position, the dot for both position and velocity representation will take a blue color. Let's put it t equal to 0. At t equal to 0, it's on the right extreme, 45 centimeters from the equilibrium position. So it is not yet been left, so it is 0 meter per second, so we'll put a dot here. At the next instance of time, when it is left, the object would move in this direction. So we can see the velocity is negative. It's about 0.1 meter per second traveling in the negative direction. Also it is on the right side, hence the color of the dot is red. It is approaching the equilibrium position. So once it approaches equilibrium, and at equilibrium the position is 0 and the velocity sees a maximum. So it is traveling in the left and sees a maximum, and once it crosses it, again its velocity is decreasing, as we can see, and it is now approaching the left end. So once it approaches the left end, the amplitude becomes maximum and the velocity becomes 0. The momentarily it becomes 0 and it changes its direction. So this is negative velocity. Now this is positive velocity, slightly greater than 0. So again this cycle continues. It approaches the equilibrium. So once it approaches equilibrium, the velocity becomes maximum, and in this case it is moving towards the right, hence the velocity is positive, and again it slows down. So this is one cycle of the oscillator. So it started with a displacement of 0.45, decreased, and then went to the left side and again came back to the 0.45. So you can see in the cycle where the object was on the left side, for half of the time the velocity was negative and for half of the time it was positive. And also we can look at the next part of the cycle where the object was on the right side, which is shown by red. Half of the time the object was traveling with positive velocity, so that it was moving this direction, and half of the time it was negative, it was moving in this direction. So if the oscillation continues, this is the graph which we see in textbook. So this is position time graph or the displacement graph, which sees a maximum and minimum. Similarly, the velocity time graph also oscillates between a minimum and a maximum. So Vmax is given by 0.45 meter per second in this case. So let us observe this in a more finer form and make this line continuous by putting more points. So the object is on the left side, this is glowing blue. Object is on the right side, this is glowing red. Similarly, the dots used to plot the graph also take the same color. Now as we know, the maximum of velocity depends on all the parameters, all the 4 parameters which are shown here. So first let us change one of the parameters, that is x0. Now for the second oscillator, let me make 65 centimeters. Whereas the first oscillator remains the same, I will not change this parameter. As a comparison, I will change these parameters, and let us see what happens to the velocity time graph. So first change, we can see the amplitude of the position time graph has increased. It is same as x0 because v0 is 0. Vmax has changed, that is it has become 0.65 meter per second. This is understandable because the spring is stretched more, hence we have given more energy to the system, and when it is at equilibrium, all the potential energy which was there is converted into kinetic energy, hence the maximum speed also changes. The phase also remains the same because v0 is 0 in both the cases. Now let us compare with some other parameters. So you can see Vmax increases. The Vmax increases, but the frequency remains the same. Now let us look at other parameters. Now we'll look at V0. If we change V0, what happens? Let me get back it to 45. And let me make V0 as 0.5 meter per second. Now when I change V0, the amplitude changes, also the phase changes this time. As we are looking at velocity, velocity is a omega, so a has changed, omega has changed, hence Vmax also changes. The magenta color, the maximum velocity is more than the green one. I can make it still higher. Now it is 1.1 meter per second. Let me get back to 0. Now let us look at the effect of the natural frequency. How do we change the natural frequency? In this system, natural frequency depends on mass and spring constant. So let me change the spring constant. Let me make it 2. So if I make the spring constant 2, the first effect is the angular frequency has doubled, the amplitude is same, whereas the amplitude for position time graph is same, but the amplitude of velocity has doubled. For green it is 0.45 meter per second, and for magenta it is 0.9 meter per second, because the same mass, when it is attached to a higher spring constant system, the energy required is more, half kx square, hence it is having more maximum speed. Let me change it to some other number. So now the Vmax has become 4 times, 0.45 to 1.8. Also the frequency has become 4 times. So in this visualization, I have visualized the velocity time graph, and we have seen that it oscillates with the same frequency as that of a position time graph. And also we have seen how the position velocity time graph changes when the parameters are changed, particularly the parameters of x0, v0 and the angular frequency k and m. I hope you enjoyed this video. I suggest you to look at the older videos on oscillations, also on mechanics, to look at the concept of position, displacement, velocity. Keep looking for this playlist where more topics and oscillations will be added in due course of time. Thank you for watching this video. Thank you.